everyone. We're going to do section 5. More set operations. Oh, and this symbol just means section. Yeah, fun fact. One of my favorite professors from undergrad always wrote those. All right, let's start with the definition. A Cartesian product. All right, a Cartesian product of two sets creates a set of ordered pairs. The first component from the first set, the second from the second set. All right, so here's how it's written. So say we have two sets A and B. We're going to write A cross B. See how it kind of looks like a product? All right, so A cross B, or the Cartesian product of A and B, is going to look like ordered pairs. So it just means pairs of elements where it matters what order they're in, such that A is in A and B is in B. Okay. Order matters. So let's talk about some examples. And don't worry, it's only 2. I know I love giving like a gajillion examples. Okay, examples. So first, let's think about the reals cross the reals. So this is the XY plane. The XY plane you learn in calculus, we know and love. We can write this as XY such that X is in R, and guess what? Y is also in R. But you have to think it's the first one and the second one. So you might be saying, well, Danica, these sets are literally the same. Does it still matter what order they're in? Yes, it does. And you know this because you know that the point 0, 1 is not equal to the point 1, 0 on our XY plane. Okay, so it doesn't matter what order they're in, even if the sets are the same. Now let's consider an example where the sets are not equal on either side of the product. Okay, let's think about A is the set 1, 2, 3, and B is the set 3 and -1. So then who is A cross B? A cross B, we just defined it, but since these are such small amounts of numbers, we can totally just write them out. Let's do it. So 1, 3, 1, -1, 2, 3. Remember, it doesn't matter what order you write them in. I like writing them systematically like this, just so I don't forget one. 3, 3, and 3, -1. Okay, so that's our set. Let's raise a couple of questions. Question 1. Is A cross B equal to B cross A? Question 2. How about the cardinalities? Is the cardinality of A cross B equal to the cardinality of B cross A? Okay, so take some time to think about these. Here is the answer. Hopefully you paused or something, or maybe you already know it. So not necessarily, meaning for general sets A and B. Okay, so for our example, that's one where those sets are not equal. A cross B is not the same as B cross A. But if A equaled B, then yeah, the sets would be the same. Kind of like our first example, where it was R cross R. R cross R is the same as R cross R. So how about their cardinalities? So let's actually talk about what their cardinalities are. So the cardinality of R cross R is going to be infinity. And then the cardinality of A cross B is 6. So if I think about B cross A, really all I'm doing is I'm flip-flopping these numbers. So I'm taking their order and I'm switching it, okay, for each of the elements. So that means that we have the same number of elements. The elements might not be the same, but we have the same number of them. So this answer is yes. So here's a cool exercise. I really like this one. So I don't know if I mentioned this, but whenever I say exercise, I mean like you can do it at home and you can bring it to office hours or something if you want someone to double check you. All right, so here's the question. Can you think of a formula for the cardinality of A cross B for any sets A and B? So if you're a little bit confused by the question, that's understandable. What I mean is if I hand you any two sets, I hand you a set A and I hand you a set B. Without knowing anything except for their sizes, do you know what the size of A cross B is going to be? So that's a fun one. I like that one. Okay, so now we're going to have a proposition like we had last video, but this one is very short. So prop is my short for proposition. So let A, B, C, and D be sets. Then first off, we have that A cross B union C is the same as A cross B union A cross C. 2, if we do something similar but with intersection, we get A cross B intersected with A cross C. Okay, number 3, A cross B intersected with C cross D is equal to A intersect C crossed with B intersect D. Whew, I always have to make sure I do that right. Lots of letters. Okay, so here are some cool propositions. These are really helpful to know. All right, another definition. The power set of a set is a set containing all, here, how about this? How about I'll say it. The power set of a set, oh, let's give it a name. The power set of a set X is a set containing all subsets of X. Okay, so what do I mean? Because that's kind of confusing. I kept just saying the same words over and over and over again. So let's talk about how it's written. So we write like this curly P or a row, but it's we always kind of write it big, equals. So here's how I like to write it. So I like to use very descriptive things. So U is a set. So here's where we can choose from. We can choose from any set that we can imagine. U is a set such that U is a subset of X. Okay, so not a strict subset, just a subset. Okay, so you guessed it, X is going to be an element in this power set. Okay, maybe that's a better way to say it. Power set of a set X is a set whose elements are subsets of X. Oh, I like that. I like that a lot better. That's a nice concise way to say it. So let's say that A is the set 1, 2, and then it has an element. That's the set, only containing 3. Okay. Then our power set of A. Okay. I like to go small to large so I don't miss any. That's always kind of my philosophy with this, because I'm always worried that I'm going to miss something. First, I'm going to start with subsets of size 0. Remember? In my first video I told you of this week, I told you that the empty set is always a subset of any set. Okay? Wow, say that 10 times fast. Okay. So we have the empty set. Now let's talk about sets of size 1. The set containing 1, the set containing 2, and you might think, well, maybe it's a set containing 3. Sorry, that was a bit aggressive. Just wanted to cross that out before someone could screenshot it or something. I don't know. So that's not a subset, it's an element. So the subset would be the set containing the element, which is a set of 3. So if it helps, when you're looking at this and you're like, that's a lot of craziness, Danica, like what is happening? You can say equals and maybe call it like B or something. And then this looks like the set containing B. Okay, yeah, that makes it a lot worse. All right, so if that's what you need to do, at least for the time being, go ahead and do it. You just want to be explicit and clear whenever you're doing anything that's being graded or anything like that or going to be read. You want to make sure that you're saying this element equals B or A or C or whatever you want to call it. Okay, so for this, I'm not going to do that, but if you want to do that, feel free, go ahead. So I want the set containing the one element, this thing. Okay, so now I want sets of cardinality 2. So we have 1, 2. We have 1, 17, 3. We have 2. and the set containing 3. So see, we already counted 2 and 1 being together, because remember, it doesn't matter what order they're in. So now, lastly, we have a set of cardinality 3, which is actually just A. Okay, so sometimes when you roll over into 2 lines, you can like do a big bracket. That's what I like to do, at least. Okay, so now the cardinality of row of A. So cardinality of A is 3. Cardinality of row of A is 8. That's another interesting problem. So if you take the power set of the power set of something, what does that end up looking like? It's not the most fun, I will admit, but it is interesting. So if you get the chance to watch someone else do it, take it. All right, the power set of the empty set. So the way that I like to think of this, the power set of the empty set, is I think about the empty set looking like that. Okay, so there's nothing in it. Because a lot of people get confused with this. So I'm going to start with sets of cardinality 0, the empty set. So now we have all the sets of cardinality 0. How about cardinality of 1? Well, we look in our little box. Nothing. And last time we ended with our set A, well, we already talked about our set. It's the empty set. Okay, so how about the power set of the power set of the empty set? Okay, so this is the same as the power set of the set containing the empty set, because we just did that calculation above. So now I go through my same process, cardinality 0. Ooh, now I have something to do cardinality of 1. And that's it. And you could keep going and going and going. So notice cardinality of the empty set equals 0. Cardinality of row of the empty set equals 1. Cardinality of row. Oh, I keep calling it row and not the power set. I'm sorry, everyone. The power set of the power set of the empty set is 2. That's an interesting problem. Okay. Now, I just have a couple of things, odds and ends, that I want to sum up for you. So let's see, what is this? I think this is section 6. Facts about commonly used sets. Okay, so the facts that we're using, if we think about the natural numbers, if any 2 elements are in the naturals, then their addition is also in the naturals, and their multiplication is also in the naturals. This is not necessarily true for division, and it's not necessarily true for subtraction either, because we don't have negative numbers. So like 1 minus 3 is not in the naturals. The integers, well, for any 2 integers, their addition or their subtraction, that's what that plus, over, minus means. I don't know if you've ever seen that. So that means plus or minus. So both options are in the integers. Multiplication is always in integers, but not necessarily true for division, similarly to the natural numbers. Okay, but rational numbers, they're good with everything. As long as we're not dividing by 0, we're good. You can add, subtract, multiply, divide, as long as you're not dividing by 0. Okay, and then a couple of definitions that we're going to need throughout this class that are very important. An integer x is even if there exists an integer k such that x equals 2k. Okay, so 0, 2, 4, 8, 16. So 16 is 8 times 2. Okay, and 8 is an integer, so that means it's even. Similarly, if an integer x is odd, then there's an integer k such that x equals 2k plus 1. You could also define this as 2k minus 1, because if you think about integers, every other integer is odd and then even, odd, then even, odd, then even. We just keep going forever and ever. So if you go 1 up or 1 down from an even, you're going to hit an odd. So if a and b are in I forgot to add that a is not allowed to be 0. Integers, then a divides b if there exists an integer L, so that's just like a cursive L, such that b equals a times L. Okay, so we write it like that, where it's like a and then an upward line b. So how that reads is A divides B. Okay? So that kind of makes sense with how we think about division. So if 3 divides 6, okay, well, really what you're thinking is 6 divided by 3 is 2, right? So it's an integer. So the way that we're talking about it here, the way that we're talking about it here is we would say 6 equals 3 times 2. So 3 divides 6. But that also means that 2 divides 6. Okay, so these are important definitions that you'll need to know.